The classic PID algorithm that you would encounter in textbooks is the form that I've written down here. We see the proportional, integral, and derivative parts indicated in what is known as the parallel form. Now, it is important to realize that this part is actually not physically realizable. We cannot calculate a pure derivative. But there are also some challenges in implementing this in discrete hardware, because in continuous hardware, typically we would use a capacitor for something like this. We could build a device that stores the integral of the error, and we could build a device that approximates the derivative relatively well, but all of this is assumed to be continuous. And the first PID controllers were all completely analog. Of course, in our modern day world, everything is digital, and so we're going to be talking about how to approximate this PID algorithm in discrete form. So the first part of the approximation that we need to do is the integral approximation. And really the part of the approximation that we are going to be focusing on is just the part that is inside the integral here. So we only really need to worry about that integral of time. The multiplication is easy to do. And so assuming we have something like our error varying over time, we could of course think of this integral term as being the area under this curve, so all of that area. But if we were approximating that in a discrete fashion, and we had only the samples at multiples of delta t, so if this was delta t and so on, then we would be able to construct a sum approximation of that integral. So at the sampling points, each one of these, this would be e k, and this would be e k plus 1. And the surface of one of these blocks, so if I just look at, let's say that block, this dimension here is delta t, and so the surface of that block would be e times delta t. And if I had to add all of them together, so that would be e of whatever the amount was, the time was, and all of these together, all of the integral together would be the sum, and I could just use something like j to k, e of j delta t. Now for the derivative part, so if we think again about what the derivative is the pure derivative at a point would be that tangent slope. But again, if we don't have, so this would be at time, if that is time k, then this would be ek, and we could approximate that derivative again by using a finite approximation. And here we have k minus 1, ek minus 1, and so this slope is now ek minus ek minus 1 over delta t. So now we're ready to put all of that together for the kth time step, and so we can write pk is still p bar plus kc ek, but now we have our approximations, 1 over tau I times the sum over j of ej going up to k there, that's j, times delta t, and that's the plus tau d times our difference approximation, so that's ek minus ek minus 1 over delta t. So this form is known as the position form because at any given time we know exactly where the output is. Unfortunately, there are some issues with implementing the position form, most notably that the sum is prone to what is known as integral wind-up. So just like the analog form, this integral can keep increasing even if the output is not actually changing. So we can protect ourselves against that by using the so-called velocity form. Now, the velocity form is simply obtained by, now you can kind of do this in two ways. You can write out the same equation twice, once for pk and once for pk minus 1, and then subtract them from one another. Or you can just tell yourself that you are taking the numeric derivative, and so if you are applying the same kind of formula that we applied here, the difference formula to obtain the derivative of e, now we have the derivative of e, we have the just e itself in the integral part, and we actually have the second derivative of tau d. So we then solve for delta pk, and this term falls away, and we are then left with kc times ek minus ek minus 1, and that's effectively the proportional term plus delta t tau I ek, because now we just have the derivative of the integral term, and for the second derivative you can verify that this is true, that the first order approximation of the second derivative takes this form. And now we are going 2 steps back in that form. Right, and so that is the derivative term. Now, a big benefit of this velocity form is that we now no longer need this controller bias that we needed in the position forms, and because we can read back the move that actually happened, if the control variable is just sticking at one point, this form will not suffer from integral wind-up.